PoliTO, Polytechnical University of Torino, from Italy.
Hello, everyone. Can you hear me?
Yes.
Perfect. All right. Um, so just to start, I wanted to introduce very briefly the team. So we're 5 undergraduate students. 3 of us have a background in electrical engineering and 2 of us in computer engineering. And our supervisors are part of the energy department at PoliTO. All right. So let's start with a bit of history of research on submagnetic materials at our institution. So there's been a lot of research going on submagnetic materials used in various applications. So a lot of computational electromagnetics, a lot of numerical models on nonlinear and hysteretic behavior of materials. So in our approach, it was just fair to like start from a more of a physics-based approach. And also, I want to mention that this was like we were pretty new to machine learning stuff. It's actually our first project, so it was the first thing we ever did, but it was very fun to learn about it. So yeah, we wanted to keep it as simple as possible. And we definitely wanted to use a composite waveform hypothesis for trapezoidal signals, simple machine learning model, and something like loss scale between different waveforms that we will see, and also keep consistency with the physics that happens in soft magnetic materials, and to use Python as a framework for everything. All right, so let's start from our flowchart for our algorithm. So let's just start. We get the input data, and we use a waveform recognition by studying the crest factor and the form factor. And we start from triangular data, which we get the results by using our first neural network, which we call neural network A, which also works for sinusoidal data. Actually, we scale the results, and we will see how, and we get also the results for sinusoidal signals. Then we move on to trapezoidal data that we have divided into two different ways. For the first kind, we use CWH, and we get the results. So by still using triangular waveforms. And then for other type of triangular data, we just use another network. So neural network B. All right. So triangular waveforms are pretty straightforward. We just use a neural network, which has this scalar inputs, and as output the energy loss per cycle, which is then multiplied by the frequency at which you get the power. So pretty linear. Then this is the very interesting part. So we actually know from some physics that we can like if we assume that the energy loss is related to the second power of the derivative, then the ratio between sinusoidal and triangular losses is just pi squared over 8. This is actually not easy to generalize because it depends on a lot of things, temperature, inductions, frequencies. But it's actually true that at some point it converges. And in this graph, we see that the red line is this value of pi squared over 8, and it converges for higher values of the peak induction. So this is a pretty interesting thing to use. So we just decided to use one of the simplest AI out there, so just a support vector machines to scale the triangular losses to the sinusoidal one. So this model some way like works. Yeah, so we use the scalar inputs, and again the output is just the energy, and then frequency, like multiply the frequency, we get the power. All right, then we move on to trapezoidal waveforms. So at the start, at the beginning, since we wanted to use some more physics methods, physics models. We wanted to use CWH for everything, but then it resulted to being very hard to use it for every waveform because of relaxation losses and relaxation effects. which are really, really hard to model. So we decided to split the two trapezoidal waveforms based on their derivative, on their different segments. So if a trapezoidal waveform has a quasi zero derivative segment, then it's just it becomes a type 2 waveform. If it hasn't got a flat part, it's type 1. And for this type 1 waveforms, we use CWH. This division is done on a threshold that we have defined. And yeah, so we just reuse the first like neural network A to just get the results. The problem is that we can get equivalent frequency in the standard CWH approach that exceed the boundaries of frequencies present in the dataset. So for frequencies that are higher than the maximum frequencies, we just rely on the neural network. But for frequencies that are lower than the minimum frequencies, we just know that that like the lead-in loss mechanism is just hysteresis, so the energy loss is constant. So that's pretty good. The only different approach to CWH is that we do it in a more of a continuous way. So we don't use the actual segment that you can see in the picture. We use a smaller segment. This takes more computational time, but it's way more accurate. And yeah, so the good thing that there's no need for an additional neural network. We just use the old one. All right. Second type of waveform, as you see, there's a flat part. So it has been recognized as a type 2 trapezoidal waveform. And here we use another neural network, which has this scalar input. And comparing it to the first neural network, it hasn't got the duty cycle. It has the RMS value for the derivative. And then again, energy loss per cycle as the output. And this is the structure of the neural network. All right, these are the total parameters. As we said, we wanted to keep it as simple as possible. And we think we in some way got the result. So around 600, 700 parameters per material. And let's see the results. These are the results for the training set. You see they are pretty good. It's only this relaxation effect that cause an issue in the CWH approach for the first type of trapezoidal signals. And yeah, and again, for a comment of the total method, there's this compromise between accuracy, computational time, and simplicity, and different approach for each waveform. Limited amount of input parameters, which we're pretty happy about. And where possible, we just use the triangular waveforms as the building block. So we use them again for sinusoidal with the square vector machine, and also for the first type of trapezoidal. And again, we couldn't just merge all trapezoidal signals. We had to divide them in no near zero derivative segment and with near zero derivative segment. Okay, I just wanted to I'm really grateful for this this challenge. We learned a lot. It was very fun. It was hard, definitely hard, but we're pretty happy about it. So if you have any questions, just ask. I'll try to reply. Maybe my colleagues are better than me in computer things, but we can try, definitely try. So thank you.
Yeah, thank you, Marco. This is also my first machine learning task. I was
Perfect.
Following what they are doing, and I was trying to figure out what's the most interesting question in PoliTO so we can do it. And that's where we are now.
Yeah.
So we are all rudimentary machine learning developers. But yeah, congratulations on developing this hybrid model. We characterize your model as one of the hybrid model sitting between neural network and machine learning. And I will ask the same question to all of the sort of hybrid and analytical models. Looks like you have different number of parameters for different material. So how much of that is human decision and how much of that is like machine algorithm determined?
Okay, I'll probably move this question to to some of my colleagues if they want to reply.
Yeah, hello everyone. I am Luigi Solimane. And yeah, in this case, we try to fix the size of parameters for the neural networks in terms of the available data, and also our trade-off compromise in terms of accuracy of the model and also model size. So on the side, we have a human control, let's say, on the size of the neural network part, which has always the same dimensions for the 5 material. And regarding the support vector machine, we decided to optimize the hyperparameters of the support vector machine's algorithm, and also to find a different number of support vectors in terms of an optimization. So more machine decided in this term, less human decided, because with the support vector machine, each shape of the ratio between the sinusoidal and the triangular waveform is different from between the different materials. So we decided to do an optimization in this term to fix the right size for each material model.
Understand. So this mostly come from how the training data was provided. If all the material were provided in a similar way, then maybe the parameters will look similar.
Yeah, of course. Of course, yeah.
Okay, understand. So it's the problem we created.
Yeah.
Okay, great. Any question from the audience?
Yes, I have a question. I see that you use the composite waveform hypothesis, which is something that I also use, which I think it's easy to use and works great. But you say that you use more segments than just 2, right? I'm assuming you use like if you have a triangular waveform and you have 2 segments, you can divide each segment in more, and you use the different flux derivative for each segment. I assume that's the thing you're doing.
Yeah, we computed the equivalent frequency for each data point of the flux density waveform. We computed the equivalent triangular loss for the equivalent frequency by assuming the derivative of the flux density of this particular segment of the triangular waveform. So yeah, it's related to the derivative of each segment of the triangular waveform.
Oh yeah, that's a very nice idea. So it fits quite well with what in theory should get. And yeah, that's actually quite easy way to implement and achieve a much higher accuracy than just 2 segments. Yeah, that's actually a very good idea. Thank you.
Okay, thank you.
Any other question? Comments? No? Okay. Now let's move on to the next team. UTK from the United States. University of Tennessee, Knoxville.
Hi, Dr. Minji.
Mm-hmm.
Thanks for letting us.
Sure.
Let me share my screen. Okay, so I believe you can see my slides.
Maybe Marco, you need to stop sharing. Yes.